Hello and welcome to my demonstration of the CSC8503 coursework. What I'll do to start is I'll have a playthrough of both levels without a voiceover, and then I'll go into the debug options and show what's going on behind the scenes. Level 1 represents our obstacle course, which contains platforms, obstacles and enemies which the player must navigate to win. At the start of the level, we can see one such enemy, our behaviour tree enemy. This uses a behaviour tree to make its decisions. It starts in its idle phase at its starting position for a random amount of time. Then, it will travel to a random area within its region and begin to raycast. If, while raycasting, it finds an object of interest, which could be a player, item, or power-up, it will then head towards it. Once collected, it will then return to its starting position and repeat the process again. If it did not find an object, it will return to its starting position and go back to its idling phase. Here we can see that the enemy found and raycasted the power-up object, picked it up, and repeated the process again. Here we have an example of a state machine object, our platform state machine. This alternates between two states that move it in certain directions based on its start and end position. Upon reaching one of those positions, it will then switch its state and move back to the other one. Here we have an obstacle generator. This will generate random objects at its location and send them down the ramp to collide with the player and knock them off. Here we have our ice floor object. This is exactly the same as a regular floor object, except that its frictional constant is 0. What this means is any items that interact with it are not affected by friction, and therefore their linear and angular velocities are unchanged as objects roll across it, whereas regular floor objects do have a frictional constant, and so objects will appear to roll and be slowed down due to the effects of friction. Here is an example of another obstacle generator that sends spheres at random locations with a certain velocity down here. These are our trampoline floor objects. These are exactly the same as regular floor objects, except this time the elasticity constant is different. Here we can see that it is 8. What this means is, anytime an object interacts with it, the resulting coefficient of restitution is much greater than it would be for a regular floor object. As a result, objects gain kinetic energy, and allows objects such as players to make these jumps here and land on the platform. Here we have a rotational cube object. This has an inverse mass of 0, and therefore is unaffected by gravity. Every single frame, it has its orientation changed across its axis in order to try and knock the player off. Here we have spring objects. These are regular objects, but this time have an additional penalty method for its impulse calculations. This means that there is always a constant force applied to it for its resting position, and therefore they're harder to push than regular objects as there is always a force in the opposite direction. Here is another example of an AI agent. This time, this one uses a state machine, and this is our patrol object. What he'll do is he'll remain in a state where he patrols across his locations and will repeat the process in the other direction. He will raycast every second, and if he finds an object of interest, he'll then proceed towards it. If he falls off the platform, the object falls off the platform, or his timeout reaches 0, he will remove that from his list and go back to patrolling. Here is another example of a platform AI. Here we have examples of constraints in action. Every single object is affected by the constraints of the other objects, and we can create a bridge-like construct through this. As a result, whenever a force is applied to one of these platforms, it is reciprocated across the entire bridge. And as a result, we can create a bridge-like structure, and as the player moves across it, all of the platforms will move. And finally at the end here, we've got our oriented bounding boxes which the player can roll down into the finish object here. Upon reaching, the player will win the game. Otherwise, the player will time out and lose, or if the AI reaches this, they will also lose. Level 2 is our maze level, where the player can play against a selectable number of AI agents to try and reach the center tile first. These AI agents are a bit different than they were previously though, and this time they use a pathfinding A-star algorithm to try and find the best solution from the start to the destination. However, they all react a bit differently to each other. As we can see, the AI on the left has followed a different path to the AI on the right. This is because while it follows the same A-star algorithm, it does not take costs into account. This means that the cost of floor, spring and ice tiles is all the same to it, and it does not care. It purely goes on a distance basis. The AI on the right, however, does care about costs, and it knows that ice and springs are less ideal to go across as they will cost valuable time. All the AI will also raycast and try and collect objects to increase its speed. Let's see who finishes first. As we can see, the AI which did take costs into account finished the destination first, so even though they followed a longer route, they were the first to reach there in the shortest time. Now I will briefly explain how the menu system works. The entire game is based on a pushdown automata with 3 states: intro, level, and pause. We are currently looking at the level state. Whenever we are in a game, if we press P, we push down the pause state onto the stack. This pauses the current game, and will not do anything with it until we pop that pause state back off the stack and return to the level. Then, whenever we exit a level, we pop that current instance off the stack and we create a new intro. What that does is it will create a new game entirely and push that back onto the stack. Then, whenever we press escape on the menu state, that will pop the current instance off the stack and exit the application. I will show this in action. During a level, we can press P at any time. This will pause everything that's currently on screen, and we are currently in the pause state. We will remain here until we pop it back off by pressing P, which I'll do so now. Then, at any point we want to exit the game, we can press escape. This will destroy the current game class and make a new one, and return us to the level state. We can also do this on the other level as well. Then, if we are on the menu state and we hit escape again, this again also pops off the current level state off the stack. However, because we are on the menu, we now just return and exit the application.